on science. If you had a class from me in the past few years, you've probably heard some version of this lecture, but this one will be a little different. I'm actually going to spend 2 days on it this semester. Most of you, I think, are computer science majors. How many are not? Anybody who's not? What are y'all? I know math. Computer engineering? Is this required for a CE? No. Okay. Elective for... Okay. All right, I hope you know what you're in for. So, most of you are computer science majors, and if you're not a computer science major, you're probably some kind of engineering major, and most people, even if you walk down the hall, find even a CS faculty member probably, but certainly most students, and say, what is computer science? And why is it called that? And what is its relation to related things? Software engineering, programming, and so on. They will not be able to give you a coherent answer, and they probably ought to be. It probably benefits you to have a picture of how what you're doing fits in with other related things in the world. So I'm going to talk about science in general and computer science. And the theme of today is just what is science? Part 1. There are 2 parts. One part is science is defined by its aims and its methods. What are we trying to do, and how do we do it? Both of those things are distinctive here. Both of those things are distinctive. I wonder if I have a remote control. So today we'll talk about the goals of science. What is it that you do here? Or Spartans, what is your profession? That should ring a bell, I think. If it doesn't, you just think I'm really crazy. So some people call boxing the sweet science. A lot of people call it that. Is boxing a branch of science? It's a good question. Not really. Here are the reasons. First of all, most important reason. Boxing is a game. What does a game mean? We made it up. We made the rules. We could change the rules. The Boxing Commission meets every once in a while and changes the rules. And when the rules of boxing change, good strategy in boxing changes. When the rules change, you might want to do different things. There are other kinds of boxing, like there's kickboxing. More stuff is allowed. You wouldn't stand the same way. You don't time your punches the same way. When the rules change, the strategy changes, the principles change, everything changes. We made it up. The Boxing Commission of each state sets the rules of boxing in that state. But there's no gravity commission, no electromagnetism commission, no periodic table commission that decides what's in the periodic table. We discover that. It's beyond our control. Nature is exactly what is beyond our control. We don't make those rules. So there are rules that govern our interactions with the world that no human institution has the power to change. Rules like the laws of motion and electromagnetism, Ohm's law, Hooke's law of springs, that we do not have the power to change. And those are the laws that we try to discover in science. And that's why boxing, the game, isn't a science. There's another thing, though. When you study boxing, you're really not, at the end of the day, at a good day in learning to box, you don't probably have new declarative knowledge, propositions you can state that you now suddenly know are true. It's more about how to. And that's the difference between engineering and science. An engineer at the end of a good day says, I know how to build this artifact so that it behaves in the way that I want. Now there's a relationship between that and science, but it's not science. A scientist at the end of a good day says, I now know that. I now know that the speed of light is 186,000 miles per second for every observer. I now know that every particle attracts every other particle with a force proportional to the product of their masses divided by the square of the distance between them, so on. The difference between knowing how and knowing that. Now, how are they related? They're intimately related because it's not really engineering if you don't use science. Phoenician boat makers 2,000 years ago could make very elaborate ocean-going vessels that could sail in the ocean. but it was very sophisticated. If it wasn't engineering, what's the difference? Suppose you asked a Phoenician boat maker, why'd you make the boat that long? What would happen if you made it half as long? They'd say, I don't know. That's how long my dad made it. He told me how to do this. There's no principle that they don't open their science book and try to predict the behavior of that artifact from its design together with their knowledge of the laws of nature. And you don't do it in boxing either. So boxing differs from science in two ways. First, it's about know-how. Second, it's not even engineering because you really don't need to know physics, biology, or any of that to be a good boxer. The way you have to know a little physics to be a good electrical engineer, a little chemistry to be a good chemical engineer, and so on. Laws of nature. So it's sometimes said, sometimes by me even, that the goal of science is to discover the laws of nature. And here are some examples. They might look familiar to you if you've had physics recently. Hooke's law of springs, ideal gas laws, Boyle's law, PV equals K, Charles' law, V over T equals K. The law of falling bodies, that's Galileo's law of falling bodies, D equals 1/2 GT squared. Do those look familiar? How many of you have seen Galileo's law of falling bodies before in a class and kind of remember it? D equals 1/2 GT squared. Raise your hand. That's familiar. How high so can you see? Okay. Now keep your hand. Oh, now keep your hand up if you believe it. That's a shocker. What? The teacher is asking us if we believe what we learned in school. About half the hands went down, I think. So let's look at these. These laws are beyond our control and they make claims about the world as it is. They are propositions about the world that make claims. However, I will tell you that not one of them is true. None of these are true. Hooke's law of springs isn't true. If you take a spring and you stretch it too far, it just breaks. Those laws, the gas laws, I left out a word. The chapter in the physics book that discusses those laws, what is it called? Ideal gas laws. It's science fiction. It's not the real gas laws. They're approximately true under certain, within certain, just like the Hooke's law of springs, they're approximately true within certain ranges, but they're not always perfectly true. In fact, they're not always even approximately true, and they're sometimes not even approximately true. They're never perfectly true, and they're not always even approximately true under all conditions. What about Galileo's law, though? The law of gravity. That's got to be true, right? What's the problem with that law of gravity, 1/2 GT squared? Why is it? For one thing, if you jump out of an airplane with a parachute on, you better hope you're not falling a distance of 1/2 GT squared. You're not. I mean, if you were, then why would you be wearing the parachute? All right? If everything follows that formula. So that law is supposed to apply to things in a vacuum, but vacuums don't exist. It's physically impossible to suck all the air out of any space on the Earth. So it's not about anything real, but even in a counterfactual, hypothetical situation where you had a perfect vacuum, it wouldn't be true. Why? Remember, Newton's law of gravity says the force of gravitation is proportional to the product of the masses over the square of the distance between them. Right? Now we're talking about the distance. Yeah. That's right. The distance is going down. As this thing falls, it gets closer to the Earth, and the gravitational attraction that the Earth pulls it with gets stronger. It's not constant, like Galileo thought. Now, it's pretty constant. It's constant to probably 10 or 15 decimal places, but it's not really constant. That's not the real truth. The real truth, so you're in chapter 6 of your physics book, you're studying that, and it occurs to you. That's not the real law. It's not really true. Maybe we'll get to the real truth in chapter 7, right? The real one that really works to all the decimal places all the time. And that, you would think, would be Newton's law of gravity. So this is Newton's law of gravity, which contradicts Galileo's. How many laws of gravity are there, by the way? There are 5. Beginning with Aristotle. Now his was just plain wrong. His lasted the longest, though. Unchallenged for 2,000 years. Just plain wrong. Then we had Galileo, then Newton, then Einstein's, then quantum gravity. And they all make different predictions. They're all different. And is the last one the best? No, it's probably not true. It contradicts Einstein's, and they're both accurate in different realms. Quantum mechanics and the theory of relativity contradict each other. They cannot both be true. And they are the best theories we have, along with classical mechanics, which they both contradict it. And those are the best theories we have. So Newton's law of gravity says a particle attracts every other particle in the universe with a force directly proportional to the product of masses, inversely proportional to the square of the distance between their centers. That's about the 3rd time I've said that today. Is it true? Well, it doesn't actually say anything. Now, the next part of the lecture I'm going to go through really quickly, but if you're curious, you can read the slides, and they explain exactly why Newton's law of gravity is false. Anybody know anything about the frame problem in AI? Anybody heard of that? No. They're related. The frame problem and Newton's law of gravity are related. Basically, this isn't going to be on the quiz, by the way. There's no study questions on this. I'll never ask you, because it's kind of a side note. I just wanted it to be available, the details to be available for you. Basically, the physics book tells you there's a force. It says there's a force of gravity, there's a force of electromagnetism, there's strong nuclear forces, weak nuclear forces. But there could be other forces. It doesn't say those are the only forces. So since it doesn't explicitly say there are no other forces at work, mathematically, it doesn't really make any predictions. In order to really use the theory, in order to really use it, you have to make an assumption that those are the only forces in play. And here's the formula you would use if you did that. That's Newton's second law of motion for real. That's it fully spelled out. That's it fully spelled out. Let me tell you what I mean by fully spelled out. This is probably important. Pop quiz. The hypotenuse of a right triangle is 30 inches long. One of its legs is 24 inches long. What's the length of the remaining side? Anybody know? I would pay for this, but I don't have a dollar bill. 18. It's 18. How'd you know? Right. 30 squared minus 24 squared. You take the square root of that. The principle you applied is a name. The Pythagorean theorem, right? Probably the most famous of all theorems. Quiz question 2. Can anybody state it?
Squared plus b squared equals c squared.
Not even close. And here's why. That is the most common answer, by the way. Is it not a squared plus b squared equals c squared? That's what we always wrote on the board. Oh, no. All right, I'm just going to hand wave this. Take a square. It's a square. All the sides have equal length. All the angles are 90-degree angles. Call the sides A, B, C, and D. Does a squared plus b squared equal c squared? No. Theorems are supposed to be true, man. Theorems are supposed to be true sentences about the world of mathematical objects. A squared plus b squared equals c squared is not one of them. The Pythagorean theorem has something to do with triangles, I think. Pretty close. She said in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. One little problem with that. What kind of thing is the hypotenuse of a right triangle? A line segment. Okay, so let me ask you a few questions. Number 6, is it even or odd? Even. What about the Pacific Ocean, even or odd? It doesn't make sense. What color is the number? Is the number 6 male or female? Doesn't have that attribute. What's its area? Doesn't have that attribute. Is it positive or negative? It's positive. Not everything makes sense to have just any attribute. Now, you talked about squaring and adding things. Can you square a line segment and add it to another? No. Numbers. Length. It's about the length of the side, not the size. So the real Pythagorean theorem says, in any right triangle, a square of the length. Well, you could say if A is the length of the hypotenuse and B and C are the lengths of the other two distinct sides, then A squared plus B squared equals C. That's the full out Pythagorean theorem. Now here's the deal. Very few people know that. Very few people have any chance of correctly stating the Pythagorean theorem. But almost everybody can solve, not everybody walking down the street, but everybody in college CS classroom mostly, can solve the triangle question. What's going on that they can't say how they're doing it? What's going on is we can't... Let me digress for a second. Anybody know how to ride a bicycle? Okay, you know how to ride a bicycle. How do you do it? In other words, how do you ride in a straight line without falling down? How? Yeah, good. So say I'm 5 years old. I'm about to get on a bike. Okay, Uncle Matt. How do I do this? Big help, Uncle Matt. Okay. People don't know. There was a guy in one of my classes a few years ago who was the captain of the Texas Tech bicycle team, national champion bicycle team. And he didn't know. Okay, most people think, this is what my dad told me, if you start to fall to the right, lean the other way. There's this thing called the law of conservation of momentum, that when you move your head that way, your hips go the other way. And I fell a bunch of times. That didn't work there. What you really have to do, there are advanced techniques, but the beginner technique is when you start to fall this way, you have to turn the steering wheel into the way you're turning, and then wiggle it back to get on course. How many people knew that? No one. How many people can ride a bicycle? Everyone. We don't know how we do things. Here's another example. In judo, there is a move called osotogari. Every coach will tell you that osotogari begins, right-handed osotogari, by stepping forward with your left foot. But nobody does that ever in a tournament. It doesn't work. The first move in osotogari really is exactly the opposite. Back with the right foot so you can lunge. Nobody says that. Everybody does it. Most of the time, we're doing things that we cannot say how we do them. And you know that better than anybody because you're a computer programmer. You know how to play tic-tac-toe, solve a matrix, do all the stuff, write code to do it. Oh, that could take all night. I might get stuck. I can do it, but I can't say exactly how I do it. That's how people operate mostly. A lot of our knowledge is habitual know-how that we cannot formulate clearly and precisely how we do what we do. We don't know. We have these habits and skills any more than a rabbit could tell you how it runs. Well, more than that. But part of what we're doing has that character. We just don't know what we're doing in the sense that we can't articulate. So people operate with a combination of declarative know-how and habitual declarative knowledge and unarticulated know-how. The principles they use they say they use are only part of the story. And it's far more true in physics than in math. So if you took Newton's second law of motion, it's F equals ma, right? No, that's like a squared plus b squared equals c squared. That's just a formula, remember, that you bring to the table with a certain skill of how to actually apply it. If you wrote it down completely, the way I stated the Pythagorean theorem completely, in a way that really logically entails the solution, it looks like this. It's way more complicated than we thought. But here's the problem. This assumes there are only 4 fundamental forces. That's probably not true. Probably, over the next 1,000 years, there'll be discovered some extra forces we don't know about. So the second law of motion is not true, and the law of gravity is really just part of it. The law of gravity is just part of that equation, which is not true. I don't think anybody, I haven't asked them, but I bet nobody in the physics department would bet that over the next 50 years they won't discover another fundamental force. In other words, nobody would bet that Newton's second law of motion, as stated fully, is actually true. So it goes on the list with Charles' law, Boyle's law, Hooke's law of springs, Galileo's law of gravity. None of them are true. So we know that some of the laws of physics are not precisely literally true, but if the most fundamental laws, those of gravity and motions, are more guidelines than actual rules, then it's likely that science has this character through and through by its nature. It's just not true. Not exactly. So what are we doing here? If it's not true, why learn it? That's a question. You can use it profitably as long as you understand where to apply what principles, when they'll work and when they won't. And here's what I mean by work. Here's a dramatic illustration of what I mean by work. If you fire a mortar at an enemy position, usually you don't hit them the first time. It hits somewhere near. And you have somebody watching from a helicopter, mountaintop or something, and they radio you. And they'll say, that was about 400 yards south of the target. Then you make an adjustment, and with your second shot you get closer, maybe your third shot hits. But there's a device that the American forces have that when a mortar shell comes in, it takes a radar image of that incoming shell at 3 different places, writes an equation through those 3 points, traces that equation back to the ground level where it came from, and automatically, electronically, fires a shell back, taking out that mortar and its operators before they fire a second shot. I mean, before their shot even hits the ground, it is coming. Now, the equations that govern the firing of that mortar shell, the friendly mortar shell, probably use Newton's law of gravity, the drag equation, and that's probably it. Neither one of those are true, and there's a lot of other things going on. The wind could change directions in the middle of flight of the thing. There's relativistic and quantum effects that we're not considering, and somebody could sit there and argue about that for a long time. But at the end of the day, the question is, are you dead or is the enemy dead? And if the enemy's dead, instead of you, it worked. So we don't scrap these things because they work. But we have to understand their limitations. We should not operate under the illusion that scientific principles out of any physics book or any book are the gold standard of objective truth. They're not. They're approximations of reality, like everything we say. I don't want you to be tempted, though, to not take them seriously because they are approximate. That is a serious temptation. It's all good, man. Everything's just an approximation. You know who the most honest? There is different people in different professions have different levels of honesty and humility. Humility in a good sense. Humility means really wanting to know the truth. Really wanting to know the truth. The most truthful people in their profession are boxers. They are at this end of the spectrum. Boxers. The least truthful people are salesmen and attorneys. Salesmen and attorneys. I don't mean they're dishonest in their private lives. I mean, at the table where they work, they're full of it. And in between, you have scientists, engineers, attorneys and salesmen, scientists, engineers, boxers. What's the difference? Why do they fall that way? It's because Attorneys and salesmen succeed by being believed, and boxers succeed by being right, and so do engineers. Scientists kind of succeed by being believed too, but engineers succeed by being right. If your stuff works, you win. Your contract's fulfilled. And if nobody believes it and it still works, you're still pretty good. A boxer, boxers are really honest. Nobody listens like a boxer. If they have reason to think you know something they don't know about what they're about to do, they will listen. Because if they're wrong, they get punched in the mouth right now. They really want to know the truth. There's nothing like the threat of being punched in the mouth right now. It is more motivating than the threat of maybe dying next week. A boxer will train harder for a match that he has on Saturday than a police officer will with his pistol that he may have to use to save somebody's life, maybe, in a month. Much harder. Most cops actually only shoot their guns twice a year when they have to qualify on that. But somebody who's competing for a little trophy, competitive shooters, they practice every day. Because the match is Saturday and they know it. That's kind of a side note. So Mike Tyson said everybody has a plan until they get punched in the mouth. The better a grip you have on reality through some set of theories, though they may not be exactly true, the fewer punches in the mouth you have to take. And people who really have to live with the consequences of their decisions, people who really have to live with the consequences of their decisions, take their beliefs very seriously and try to have the best ones they can. So, what's the job of science really? This is not exactly what I want. Okay, the aim of science is to discover theories that help predict, explain, predict, and control the natural world. I changed that on another slide, but not. The aim of science is to discover theories that help explain, predict, and control the natural world. The natural world is the world beyond our control. We don't make the rules of gravity and electromagnetism or even algorithms. We make algorithms, but we don't make the laws that govern what they do when we turn them loose. These theories are always only approximate, but some approximations work better than others for some purposes, and we better know. And we better be right. For example, if you use Ptolemy's model of the solar system and Aristotle's law of gravity to navigate a satellite to the largest moon of Jupiter, you just fail. It doesn't work. You really need to use Kepler's laws, Kepler's model of the solar system, and Newton's law of gravity. They work. They're not exactly true, but they will work. They will get you to Jupiter. That was a little digression. That picture is a picture from a Sumerian temple. And it's the Sumerian sky god, Lotan. Or, no, this is Hadad, and this is Lotan. 1, 2, 3, 4, 5, 6, 7. 7-headed dragon, water dragon. Almost every religion incorporates a version of what's Chaos Kampf. Anybody speak German? Not one. Yes, what does it mean? Chaos Kampf. Fight against chaos. Almost every religion has this in their story of creation. Not just somewhere, but in the creation story. There is a water dragon, usually female, usually associated with the deepest parts of the ocean, the parts of the ocean that primitive people couldn't fathom at all, had no idea what kind of monsters were down there. Total unknown. And the god of the sky, usually. And there's a fight. And the sky god kills, slays the water dragon, the chaos monster, very often many-headed chaos monster. The sky god slays the chaos monster and forms the world from its remains. This happens in Sumerian religion, Babylonian, Marduk and Tiamat, the Babylonian version. If you play Dungeons and Dragons, Tiamat is a thing in D&D. When in the height heaven was not named, this is from a Babylonian scroll, and the earth beneath did not yet bear a name, and the primeval Apsu who begot them, and Chaos, Tiamat, the mother of them both. Their waters were mingled together. Tiamat is this water dragon in Babylonian, but it's also the depth of the ocean. Same word. The depths of the ocean personified as this many-headed water dragon. In the Greek, ancient Greek religion, you had Zeus and Typhon. In Norse, you had Odin and Ymir. In Hindu, Indra and Vritra. All very similar stories. Now, I said almost every religion. Did I leave some out? The Abrahamic religions, Islam, Christianity, and Judaism. Do they have the chaos come in their creation story? Yeah, they do. Genesis 1:1-2. In the beginning, God created the heavens and the earth. Now the earth was without shape and empty, and darkness was over the surface of the watery deep. But the Spirit of God was moving over the surface of the water. So you have the Spirit of God, the surface of the water, the parts that you can see and understand, and you have the watery deep. But the Hebrew word for the abyss, the watery deep, tehom. That's the Hebrew version of the Babylonian word Tiamat. Same meaning, same pronunciation. Isaiah 27:1. The Lord will punish with his sword, his fierce, great, and powerful sword, Leviathan, the gliding serpent. Leviathan, the coiling serpent, he will slay the monster of the sea. Leviathan is Lotan. This is mentioned in Isaiah 27:1, in the book of Job, and twice in the book of Psalms. A battle between God and Leviathan. So why does almost every culture in the world have the same story? That the world is formed in this battle between the Father of the sky and the water dragon. There's a guy named Jordan Peterson. Anybody ever heard of him? He's a psychologist. And he studies comparative religion and psychology and archetypes, things that appear in every different culture. And this is what he says about it. Something we cannot see protects us from something we do not understand. The thing we cannot see is culture. The thing we do not understand is the chaos that gave rise to culture. We have agreements with each other of certain laws and rules that we hold sacred and enforce collectively. And we take some of them very seriously. And they're not perfect or close to perfect at all. But what is life like without them? We don't know. But apparently, so Peterson says, if the structure of culture is disrupted, chaos returns, and we will do anything to defend ourselves against that. If you want a little glimpse of what it's like, you can Google and see what happened in Toronto. At one point, the police, for one day, went on strike. No law. It's all good, man. Do as you please. Imagine all the people living for today. It wasn't as cool as you might think it would have been for there to be no rules. It was what you'd call a state of war in the streets. Probably anything is better than that. So the agreements that we make with each other, though they are highly imperfect, give us a handle on our interactions. And I didn't point this out, but the whoever slays the water dragon in the creation story is the primordial lawgiver. More than anything else, they are the lawgiver of the universe. So they are usually, it's usually a very imperfect. Zeus was very imperfect. Zeus was a cheater and a liar and just sort of a regular guy. In fact, Odysseus in the Iliad is called the equal of Zeus in council. Zeus is no smarter than the smartest person. But somebody's got to be in charge, or something, or some force needs to regulate what's going on. And the same thing in our knowledge of the rules that govern everything we do in the world. We need a grip on it. It doesn't have to be perfect. It just shouldn't be total chaos. We need some understanding, some imperfect understanding, and we're constantly fighting the battle. We are constantly fighting the battle to not perfect but improve our theories. Now, what do these theories look like? They have three parts. This is a quiz question. So the aim of science is to discover theories that help predict, explain, predict, and control the natural world. Theory has three things: vocabulary, axioms, and interpretation. Vocabulary is what are the key words in this theory. For example, in classical mechanics, you have force, mass, time, distance, etc. Axioms. What's true? What do we assume is true, stated in terms of these key concepts? In classical mechanics, you've got conservation of momentum, conservation of energy, Newton's laws of motion, the law of gravity, the drag equation, etc. Now, the one that is not talked about very often, interpretation, the conditions under which to apply the theory, methods for interpreting its vocabulary in the world of experience. Classical mechanics pretty much applies when things are not moving too fast, they're not too big, they're not too small, and they're not being deformed, and they're not undergoing a chemical reaction. Things are intact, like billiard balls. They just bounce off. So three elements of a theory: vocabulary, axioms, and interpretation. Vocabulary is the most important. The most important kind of knowledge is the knowledge of what is the same and what is different. The most important knowledge is actually the difference in different people's worldviews. Republicans and Democrats don't differ so much in the propositions they believe are true. They differ in the way they see the world and what they see as alike and what they see as different. What categories they put in. Let me give you a scientific example. I know we're about done for today. Well, I'll just pick up where I look at the study questions over the weekend and the slides, and I'll pick up on Monday where I left off. What's most alike, a swallow, a bat, or a whale? Which one's different from the other two? The swallow? It pretty much looks like the bat. If you told a mech or come by villager that a bat and a swallow are the same and a whale is different, they would think you were totally nuts. But here's the thing. This is the last thing I'll say today. Suppose you've never seen a bat before, neither had they. And the bat flew up and it landed. And you said, "That's the weirdest looking bird I've ever seen. That is a weird new kind of bird." But then you look a little closer, and the mech says the same thing. But you look closer and say, "Oh, wait a minute. It has hair on its ears, not feathers." If you know a little biology, you know now a lot about that animal. It's not a bird. So what? Here's so what. It doesn't lay eggs. It doesn't build nests. It bears its young alive, and it feeds them with milk. It has 3 bones in its inner ear, like a swallow, like a whale, but unlike a swallow. And its brain has the same components as that of a whale. They're just a lot smaller, different from a swallow. You know that without cutting its head open. You know that without seeing it have children. You know all that just because you know categories to put things in that allow you to make generalizations. All the laws of science are generalizations, but you can't make generalizations without categories. Generalizations are about categories, like all dogs are alive. So having things in the correct categories, knowing what's alike enough to give a name to similar things, is the basis of being able to state the law. All right, that's all for today. Check out the homepage, check out the study questions, quiz next Friday. Have a good weekend.